Hey there, and welcome. When you hear the word acid, what pops into your head? Probably bubbling beakers, maybe something dangerous and super sour, right? Well, you're not wrong, but that's just a tiny piece of a much, much bigger story. So what exactly is an acid? Let's get into it. So to get us started, I've got a little riddle for you. What on earth could possibly connect the sour taste of a lemon, the battery that starts your car, and the actual blueprint of life that makes you, well, you? The answer, believe it or not, is acids. And by the end of this, you're going to see exactly how. All right, so first things first, let's start with the basics. The version of acids we all probably remember from high school chemistry class. These are the classic hands-on properties that, gave acids their name in the first place. These are pretty easy to remember, right? We know they taste sour, just think of vinegar or a lemon. In the lab, we're taught that they turn blue litmus paper red, have a pH lower than 7, and can fizz up when they react with some metals. And it makes total sense. The word acid actually comes from the Latin word acidus, which literally means sour. Now, this old school view is a great place to start. Early scientific definitions, like the Arrhenius theory, basically said an acid is anything that pumps up the number of hydrogen ions when you dump it in water. But see, there was a huge catch. It only worked in water. Science really needed a better, more powerful definition. And that upgrade, that new definition, came along in 1923. Two chemists, Bronsted and Lowry, working totally on their own, came up with a much bigger, more universal way of thinking about acids. And honestly, this is where the story gets really good. Okay, so check this out. On the left, you've got the old Arrhenius theory, totally stuck on water. But on the right, you have the Bronsted-Lowry theory, which was a complete game changer. It redefines an acid not by how it acts in water, but by what it fundamentally does. It has the ability to donate a proton, which is just a hydrogen ion, to something else. This new idea works everywhere, in any solvent, not just water. So this is it. This is the one thing you really need to remember. An acid is a proton donor. That's it. That simple, elegant idea is what unlocks our understanding of everything from powerful industrial chemicals to what's happening inside our own bodies. But of course, there's a catch. It turns out that not all acids are the same. You see, being a proton donor isn't a simple yes or no thing. Some acids are super generous with their protons. They give them away easily. Others, they're a little more stingy. And that difference is what we call acid strength. A strong acid, when you put it in a solution, basically gives away all of its protons. Just poof, they're gone. It's a one-way street. A weak acid, though, is much more hesitant. It only donates some of its protons, and the reaction can actually go backwards. It creates this kind of balance, an equilibrium, where some molecules are giving up protons while others are taking them right back. So let's put some names to these faces, right? Over in the strong corner, you've got the heavy hitters, like hydrochloric acid and sulfuric acid. These guys are fully committed proton donors. And then in the weak corner, you have things like acetic acid, that's what's in vinegar, and carbonic acid, which is what gives soda its fizz. They're just a lot more reluctant to let go of their protons. Okay, so now that we've got a handle on what an acid is and what makes it strong or weak, let's see where these things actually show up in our world. And we have to start with their massive role in industry. Just take a look at this number for a second. 200 million tons. That is roughly how much of just one acid, sulfuric acid, the world produces every single year. It is by far the most produced industrial chemical on the planet. That alone should tell you just how important this stuff is. And what are we doing with all that acid? Well, it's used to make the fertilizers that grow our food, the detergents that clean our clothes, the dyes that color them, the batteries that power our cars, and even to strip rust right off of metal. Acids are pretty much the invisible workhorses of our entire modern world. But their story goes so much deeper than just factories and manufacturing. Maybe the most amazing part of all is the critical role that acids are playing inside of you right this very second. So deep inside your stomach, you've got hydrochloric acid, and it's a really strong one. Its main job is to start breaking down the big, complex molecules in your food. It basically kicks off the entire process of digestion. And if we zoom in even further down to the cellular level, every single one of your cells is constantly using amino acids. These are the little building blocks your body uses to create all the proteins it needs to grow and repair itself. And this brings us all the way back to that question from the beginning, that crazy connection between lemons, car batteries, and you. The A in DNA, it stands for acid. deoxyribonucleic acid. The actual code of life, the master blueprint for everything you are, is an acid. So, what is an acid? It's so much more than just a sour liquid in a lab. From the industrial giant that builds our world to the biological architect that literally builds us, an acid is really just a proton donor, a tiny particle giver that shapes our reality in ways we almost never see. It's something to think about the next time you squeeze a lemon.